Thank you, Mr. Yudanuddin MT. I would like to introduce the second keynote chair, Dr. Khalil. Please welcome Dr. Khalil.
Thank you very much. And welcome all participants to the IC COSITE. And this is the second keynote session. And I'm Khalil Mukhtar, who will lead this session. And we are also very happy and fortunate to have another international keynote speakers from Nanyang Technological University. As we know, this is one of the best universities in the world. Professor Ng In Kui. Probably I will make sure whether Professor Ng is already with us. Hello, Professor Ng.
Hello.
Hello, welcome,
Professor Khalil. Nice meeting you. You will play the video, right? Don't mind.
Yeah, sure.
Yeah,
sure.
You are so kind.
Yeah, okay. Yeah, hope everything goes well there. So we are very happy to have you here. And let me read the short biography first. Professor Ng will deliver the topic Dynamic Synthetic Thermal Images Extraction Technique for Faint Visualization. And Professor Ng obtained a Bachelor of Engineering from University of Newcastle and PhD at Cambridge University with a Cambridge Commonwealth Scholarship. He is also elected as academician for European Academy of Sciences and Arts, and he also a fellow from several institutes, the American Society of Mechanical Engineers, Institute of Engineering and Technology, to name a few. And also he is the distinguished fellow from Institute of Data Science and AI, China. He also have a very outstanding achievement in scientific experience for editor-in-chief for 2 ISI journals, which were captured by GCR within 2 years of their inauguration. He is an expert research funding reviewer for many funding agencies, and I can mention some of his expertise, especially on thermal fluid and health-related diagnosis fields. So last but certainly not least, his ongoing work on non-contact screening for carotid artery stenosis and superficial vein finder has resulted in 3 filing patents. So there are many experience of Professor Ng, and we are happy to have him here. And for the presentation, he already prepared the pre-record presentation. So we will play the presentation shortly. And however, on the Q&A session, he will directly lead the session and answer the question from all the participants. So please, without further delay, operator, help me to play the presentation. Thank you very much. Enjoy.
Thank you, session chair. Apologize first, the recorded video a bit long, so apologize first.
Sure, it's okay.
Hello, my name is Eddie Ng. I'm from Nanyang Technological University, Singapore. Today, I'm happy to share with you on my talk for thermography-based superficial vein projection system to ease the real-time vein puncturing procedure. This is a joint project with a hospital. My collaborator is Dr. Lim. He's a cardiologist from National Heart Center of Singapore, and my former PhD student, Dr. Ashish. Right. We have published this work in this computer in biology and medicine. So for those who are interested, you can read out this paper on a method to produce high contrast vein visualization in active dynamic thermography. So what we have here is when the skin exposed to the stimulation, cooling applied for 30 seconds, for example, and during the reforming process, every fixed times, fixed temperature step of 0.5 degrees C change, we derive a dynamic synthetic image reconstruction along the rewarming path. And you can see that here, the 1, 2, 3, 4, 5, 6, 7 correspond to the image that we had developed, the synthetic image, like SI, with the time going and the contrast getting better and better. So this can reproject back to the region of interest so that you can see the vein for puncturing purposes. Right, here just showing the cost per unit graph in US dollar of those existing technology used in the market. Right, it's combination of two or more methods. You have LED and near infrared. So those are prices, right? It can range from about few $100 with LED, but accuracy is not good, contrast is not so good. But all the way from vein locator, right? Few thousand, and then up to 300,000 US dollar for non-handheld vein viewer, right? You can see the whole range. So, but this is near infrared or LED method. So none of these existing method using the thermography, thermal imaging method, which is non-invasive, non-contact, right? Method, which is novel here. The limitation of the vein projection system, right? Technology in current devices, as I just mentioned, near infrared or LED light source, or a combination of the two, right? It doesn't perform well in the case of high fat content and irregular skin surfaces, right? And these are not of much help in easing the vein puncturing procedure, and also associated with the motion artifact also. So what we're going to propose is, this is our proposal, right? We have a infrared camera, right? We have a dynamic image data transferred to the computer, but we using the active dynamic thermography approach, using the cold air stimulation instead of the hot one. Stimulate for 30 seconds, for example. Then after 30 seconds, we stop stimulation, cooling stimulation. Then the skin and the arm is rewarming. So they keep capturing this for another 120 seconds, for example. Then we have this transfer of the dynamic synthetic image, right, to the projector. So this real-time projection back into your region of interest. So this real projection, real-time, we can eliminate the motion artifact. Right? This is what our proposal. I will talk about it in more detail later on. Come back to thermography. Right? As we all know, so long as the object above 0 Kelvin, this is a third law of thermodynamics, right? It will emit infrared radiation, which is a measure of surface temperature. So we have two types of thermography. One is passive, another one is active. Passive, meaning no external stimulation. This one, the signal to noise ratio is not so good, right? So we are adopting the active thermography, which either using the external stimulation, right? It could be pressure, press on it, or heat stimulation or cooling stimulation. And this under active thermography, we have two types of it. Lock-in thermography versus the pulse thermography. We are using the pulse thermography and then the cooling stimulation. Here just to show the typical light camera picture, right? Optical camera image. Then we have a infrared imaging. Right? We have external stimulation, right? Active dynamic thermography. I repeat again, we apply cooling air for 30 seconds with different temperature. Later I will talk about the temperature effect, stimulation temperature effect, 3 of them, 5, 8, and 11 degrees C. On removal of the cooling, capturing the rewarming for 200 seconds using an infrared sensor. Right, we develop a new technique called tissue activity ratio image reconstruction method used in active dynamic thermography. This is our proposal. And as we all aware that ADT, active dynamic thermography application, you can use it for breast tumor detection, renal diseases, burn wound monitoring, cardiac surgery monitoring, right, and skin blood flow diseases. As when we expose our skin to ambient, right, when we apply the cooling for 30 seconds, temperature drop on the skin, this drop again the skin temperature. Of course, you can normalize it with the cold temperature, for example. One remove it, it's rewarming process, right? Cooling rewarming curve. This rewarming phase open to ambient convection, right? It will start happening. So this is the what we have. Here TC is the time taken for cooling, right? Then this TCIJ, when the cooling stimulation stop, and then the time taken for the rewarming to certain percentage of recovery, for example, TR, then correspond to TR, the time taken for TR, and each pixel, IJ, right? X and Y pixel, because 2D. Here to show our experimental setup and equipment use under the NTO IRB approval, right? We have the arm, left arm tripod to support the infrared camera, right? Then we have a cooling pad for stimulation. Totally, we have 14 subjects, but in this presentation, I just shown the 3 subjects, the result of the 3 subjects. Right? In that paper, we have analyzed the 14 subjects, right? Which have 24, the male of 24 plus minus 1 year, or 1 year plus minus 1 year age differences. Under ambient control, ambient temperature 21 plus minus 0.5 degrees C. The infrared camera that we use from infrared focal distance 12 cm image acquisition is 2 frames per second. 2 frames per second. Right? External stimulation is cooling through a cooling pad. This is one way. We have also the cooling air, which is a higher end. Right? The accuracy of the camera is plus minus 2 Kelvin. Pixel is 320 times 240 visualize window using the detector of microbarometer. This one just to show again the light camera, right? Human forearm visibility to the neck eyes. Then contrast to the passive static thermography, just to show the temperature. Yeah. Right? This is without any stimulation. So the vein that we have is very blurred, right? Can't tell much. Now with the sequence thermograph in the active thermography. So what we have is at initially, right, without cooling. So when we apply the cooling for 50 seconds, right, this is cooling pad. After cooling pad being removed, right, time start counting 30.5, 35, 40. This is a thermal image over the region of interest that we can see. So during the rewarming, we can see the vein, right? Primary vein, for example, primary vessel. Here is a secondary vessel, right? Start showing. But this contrast is not so good. If we apply the subtraction method, right? At 35 seconds minus the 30 seconds, we obtain this. 40 seconds minus 30 seconds, we obtain this. Right? 45, we obtain this. This help to slightly improve the visualization detail, but it's still not good enough. And from the paper that we published in infrared physics and technology under this venous blood flow characterization technique. So we have observed, we able to pick up the direction of the blood flow, diameter of the blood vessel, and then velocity of the blood. So that is what we can, you can read out from our paper in Thermography, venous blood flow characterization with external cooling stimulation, published in 2018. Right now, I share with you how we apply the contrast technique. Right, contrast is defined as contrast is W, defined as the ratio. This ratio is image parameter over the target feature. That means the blood vessel, for example, this solid rectangular box, this over the vessel surface, and then versus the image parameter over the background, which is a skin tissue without the vessel, for example. So I minus IB over IB. So this is a contrast formula, right? And we apply this contrast. The purpose is to quantitatively characterize the visibility of the superficial vein, characterize the visibility of the vein. Here I shown 3 subjects, right? Contrast versus the time after remove of cooling. Subject 1, square box, right? Yeah, the middle one. Then we have a subject 2, subject 3. What we can conclude from here, observe from here, every different individual, the peak of the contrast occur during the rewarming process, right? Occur at different time. For example, this subject 2, right? Next maximum contrast, peak contrast, occur at 40 seconds after removal of cooling. Right? So this is not much usefulness, right? If you want to generalize a result. So this bring out the need for single image, be it a static or dynamic synthetic image. Right? We have done the work some time ago using the static single synthetic image, but we know that this is for passive or even for the dynamic. You see the recovering, the contrast reduce again after the certain time of rewarming, right? Rewarming. So this is not so promising. So we're thinking of another new technique, dynamic synthetic imaging, right? With the reconstruction for ADT, right? So the contrast W of the transient images will decrease, right, as the recovery process progresses. So you can see when the recovery process progresses toward more and more, right, the contrast reducing. So this is not good for vein puncturing, right? You want to have a contrast keep increase. So that is the key, the difference that we doing, right? This means that we need a synthetic image from the ADT sequence using the functional information to ensure high contrast visualization along with quantitative information. So that is called dynamic synthetic image that we going to talk more. Here what we have is during the rewarming, right, transient image series. 0.5, 10 seconds, 20, all the way, for example, 140 seconds to 200 seconds. So every second we have 2 frames per second. That means the image that we capture is a lot, right? The frame multiplied by the frame number. So how to analyze over the area, region of interest? So we come up with a new technique called tissue activity ratio. Is defining at rewarming rate over the cooling rate. So this TAR calculation, it gives us a way to do a image construction, right? We can obtain here. This is typical example. I will talk more about the detail. So method of extracting the synthetic image. In the past, back in 2002, right, by Merla, right, he propose tau time, meaning the time taken for the recovery process to reach 63% of the before and after thermal excitation effect, right? For example, 63%, right? So this time taken for the time taken, right? For example, time taken to reach 63%, right? Before and after thermal excitation. Then in 2017, right, a Polish model, he proposed DT norm, right? DT norm, defined as the ratio of rewarming temperature difference to cooling temperature difference. Then 1 year later, this model again, he proposed T, the time, 90% minus 10 to the norm, right? So it's defined as by dividing the difference in time to reach 90% and 10% of the recovery phase by the total duration of rewarming, right? We're working together for the breast reconstruction. I will share more on this later on. But in our work here, we propose a new way called tissue activity ratio, which is the ratio of rate of rewarming to the rate of cooling. This is novel. So what we have here, for example, the rate of rewarming is defined as TR, right? This temperature TR minus the temperature when the cooling is removed, right? Divide by the time taken, TRIJ, of each pixel, right? Of each pixel. Then rate of cooling is TIJ cooling, right? TIJ, right? Minus this temperature over the time taken. So this is rate of cooling. We have a rate of rewarming. The ratio of it, right? Rate of rewarming over the rate of cooling is called tissue activity ratio. This one is very interesting parameter and useful for our work. When we compare to the tau, right? Just now I already explained the tau technique. We have a TAR, which is our approach. We apply the previous method, tau image, then inverted tau, right? Inverted tau, which defined as here. This is opposite to tau. For example, tau high, low, but inverted become low, high, right? It's for different aspect of visualizing. But you can see that our TAR approach, right? The contrast become better. Our TAR image, the contrast plus minus standard deviation compared to the tau inverted tau, right? The model method back in 2018, right? You see our contrast for subject 1, subject 2, subject 3 have been improving. For more detail, you can read our paper in this single image reconstruction in active dynamic thermography, right? A novel approach, again published in Infrared Physics and Technology back in 2018. So, however, we observe limitation of static synthetic image reconstruction. That's why we propose dynamic. So the limitation of static synthetic approach is the lead time to obtain the synthetic image is rather high, right? Because it takes the whole sequence of the image that is first acquired and then processed to produce a static single TAR image. And it suffers from motion artifact error in the final image obtained. If there's a motion of the arm, right, then it will blur the image a bit. So this again mentioned here the paper. So we propose dynamic synthetic image method. Right. What we're doing is we use a Python 2.7 library and MATLAB toolbox for image processing, SI reconstruction, and data analysis. For the statistical significance, we're using the single factor multi-level ANOVA with p-value of 0.05. In statistical analysis, we use a Microsoft Excel data analysis toolbox. This ADT image sequence, we read and store as array, right? Then we look for, try to construct the synthetic image. So just now I mentioned static, which is over here, right? Although it gives good contrast and signal to noise ratio, but it may suffer on the motion artifact if in the final phase of the image, if there's a motion, that's it, right? So we have reference time, reference temperature, right? So you go through this flow chart, then you finally find your TAR image, which is a single image when the recovery phase reduce, right? What we have next, dynamic synthetic image. So here, the low lead time with a fixed time step size of 0.5 degrees C. This faster revolving of pixel over the vein compared to pixel around the vein bring the contrast in the image. So that is a theory that we have. Right? Again, we have a reference temperature and absolute reference time taken. So with the intermediate value of the T, the time reference and the temperature reference for TAR at each pixel. So we can fix the step temperature change. For example, we use 0.5 degrees C, right? Every step change then increase by same factor in each step. Then set this as a temperature reference for each step. On the absolute reference time taken one, right? We have absolute time for each pixel to reach the reference temperature in each step, then set it as a time reference time at each step. So the two, we can find the TAR image at each step, right? This is multiple image along the recovery phase. There's a difference, right? So if we look at this dynamic SI method for three steps that I mentioned, we shown only three subjects in this talk, right? This time taken, right? Time keep increasing during recovery, and the contrast we obtain for subject 2, same thing we plot subject 3. Then, though the subject specific variability in the shape, right, size and location of the vessel, the region of interest is different. However, our live feed of the processed synthetic image, dynamic SI, right, provide higher visibility of the vein over time. You can see over the time, right? The contrast is very promising. So in our previous work that on the static synthetic approach, the contrast we found, for example, subject 1 is 1.77, right? Subject 2 is 0.78, subject 3 is 1.4. You can find from this paper. But you see when the recovery, the revolving process, the contrast dropping. Suppose we start punctured at this time after the peak, we will lose the contrast. So this is undesired. So what we using the dynamic synthetic is, you can see the contrast increase as the revolving progresses further, and this supersedes the static synthetic image contrast for all the three subjects that we shown here. So this is the right approach, right? The correct way to do, because the contrast remain and keep improving with time so that we can accurately puncture the vein, right? Right now, we also conduct this dependency of dynamic SI contrast on the temperature of the external cooling stimulation. We investigate this dependency effect. The three cooling stimulation temperature is 5, 8, and 11 degrees C was tested. So here we have before cooling, the 20 seconds before cooling, and after cooling at 50 seconds. The average temperature within the cooling stimulation zone. Right? For the stimulation temperature of 5, 8, 11, Before cooling, we have this temperature, right? After cooling, we have this. Of course, the lower stimulation temperature, right? The average temperature will be lower, right? This is expected. And now, this picture, the thermogram shown, selected dynamic SI across the whole recovery phase duration, for different cooling temperatures. So we can 7-degree progress with the recovery phase, right? And here what we've seen here, the contrast time, then so, right, seen a lower cooling temperature induce a deeper cooling effect for the same cooling duration. Therefore, the total skin mass that is need to be rewarmed increase. That means rewarming time will increase also. So in all the three cooling stimulation cases that we show here, given the relative pixel value of the nearby skin tissue is also affected by the same phenomenon. This resulting contrast value remain largely unaffected, right? So that is the observation that we have done. Now, we plot the dynamic SI contrast comparison for different cooling temperature in the same study participant. So horizontal axis is the time taken after the removal of cooling, and plot again the contrast for different cooling temperature, 5, 8, 11. What we observe here, up to 40 seconds, there is an overlap in the image contrast, W, like it overlap over here, for the three cooling temperature. But this contrast in 5 degrees C1, the lowest temperature stimulation temperature, ADT experiment, was found to be higher, right? This 5 degree higher, the contrast, followed by 11 and then 8. We apply the one-way ANOVA analysis with p-value of 0.52, we obtain 0.52. So this shown that there is no significant difference in the contrast of dynamic synthetic image as extracted for the three cooling temperature. This is promising and encouraging also. Then what we have next, we shown the overall dynamic SI contrast data of all 14 study participants across the three cooling temperature. Just now, what we shown here is a 3. Right? Now, you can see all the 14 cases, the data point. So what we have seen here, the contrasts are more concentrated in the first 60 seconds, right? As pointed, all clustered toward here, implying a decrease in dynamic synthetic image number as the recovery progresses, right? So this implies that lower rate of heat transfer, it takes more time for the image pixel to reach the fixed step change in the temperature. Here is 0.5 after 60 seconds, right? So it needs more time for the image pixel to reach the fixed step change of the temperature, right? That's the reasoning. After 60 seconds, it's stretched out, but here it's clustered. Next, we try to look at the average contrast value of the DSI extracted within a time interval. We plot also the standard deviation, plus minus SD, with time. This time, we include the fixed 20 time interval was set, 1 to 20, like 21 to 40 seconds, then 41 to 60. So every 20 seconds times that we average up for different three cooling temperature. And what we observe here, the contrast curve show an increasing trend for each of the three cooling temperature value, right? The slightly increasing trend. Here, if the contrast is 1, you can see the increasing trend with the time. So this is promising. While for the 5 degrees C case, the average value of the contrast remain below 1, right? Below 1, still 60 seconds. So below 60 seconds, right? This is a 5 degrees case, right? 5 degree case 1, 60 seconds. So up to here is all, right? Almost below 1. So this is, but however, for the 8 and 11 degrees is one, it was found to be above 1, right? Above 1 only. This is contrast of 1. They are all above 1. Above 1 is good. Less than 1 is no good, right? The contrast cannot be visible. So it's found to be above 1 after 20 seconds of the cooling application. So now I will come to almost conclusion already. Here is to show the experimental setup that we test our vein visualization technique. This I have mentioned before, cooling. So these are fixed temperatures step size that we set from 5.5, right? So we have, for example, here 1 to 7, the corresponding contrast we obtain. You can see that the synthetic image reconstruction along the revolving phase, right? The vessel, the contrast is remained high, at the same time keep improving. So we can take this opportunity to find the vein and then puncture it accurately. Now, the advantage of our technique, it increase the first attempt success rate of cannulation, right? And this is independent of skin color and independent of irregularity, insensitive also, right? As in the case of existing devices, is sensitive to this. LED, near infrared is sensitive to skin color, right? And then irregularity also, right? Due to the surface irregularity. Then effective with our technique is effective with obese skin fat tissue. We eliminate the need of a rubber band, right? As in the case of existing devices. You know that existing devices, they need the rubber band to compress then release, right? To see the change in the blood flow. So we reduce the cost of cannulation, right? Our cost, very simple, infrared, handheld infrared device is very cheap. We know that, especially in US, every day about 2.7 million procedure of this vein puncturing is required, right? So if you can, in worldwide, right, you can reduce or increase the first attempt success rate of puncturing, then that will be tremendous improvement, right? So it can reduce in pain, particularly in the pediatric patient, right? And reduce the time of taken, increase patient satisfaction and clinical staff productivity. So we eventually we will have less bruises, right? Reduce blood clot, rashes, some due to the fragile vessel, right? Fragile vessels or edema problem. Device can be used to cannulation procedure. For example, administration of steroid, drug, electrolyte, blood donation, blood taking, all this. Right? Also, the diameter of the blood vessel can be easily estimated so as to guide a robotic arm for an automatic image capturing approach. Our dynamic imaging eliminates the motion artifact in the projected image. So the application, right? Now talk about the application. The key concept here is clinical health of skin tissue is determined by perfusion in the region that is directly related to the heat transfer characteristic of the skin tissue, right? This is the application of our technique. It can apply to skin condition monitoring, skin cancer detection, venous disease detection, thrombosis versus varicose diseases, peripheral vascular diseases, right? Also condition monitoring during surgery, muscular pain detection monitoring, burn wound detection, active breast tumor thermography to increase the diagnosis efficacy, flat reconstruction success monitoring. So I have one slide to show this. Then occupational disease diagnosis for like the vibration induced white finger, or our technique can be used. So this is the work that we work with the Polish group, Model Heart, right? Using our tissue activity ratio technique. He has done using the tau, inverted tau. So after we propose this TAR, we redo their work and improve. You can see the improvement. It's during the breast reconstruction, they have a donor site of tram flat, right? Put it over the breast for reconstruction. So after the surgery, you want to check whether the breast flat will become necrosis or not. Right? If the suturing, the blood vessel cannot flow, then the reconstruction failed. Right? So there is a optical image after reconstruction. Breast is a cooling, air cooling machine. Here is a passive thermal image, but after we apply the active thermal image sequence, right, with the cooling, rewarming, so we have all the sequence. Then what we have next, we have this reconstruction of inverted tau TAR, right, tissue activity ratio image. Then in this work, although we use a manual region of interest segmentation, this ROI segmented image that we obtain using the TA, you can see the normal one with warmer, right? It's shown that the blood is flowing, and the necrosis one, right? The blood is not moving well, not flowing well. So this will eventually, it's shown that the reconstruction will be failed, right? So the work have been published in this, again, infrared physics and technology, right? Under this post-operative cancerous breast resection flat necrosis, the title of the paper. So what we have, you see our TAR approach, the cutoff value, sensitivity and specificity, right? We have subject 23 normal case, 9 disease case, right? You can see the TAR, the contrast we have, right? It's rather good, right? Because for the disease one, failure, the tissue activity ratio reduced, expected because blood flow reduced, but the healthy one, right, TAR higher value, right? We achieve the sensitivity and specificity more than almost 90%, right? And specificity 83%. So this is better than the 2018, the tau approach. Right now, finally, conclusion. I give some concluding remark. This is the first active dynamic thermography-based vein visualization image projection method in real time for human subject that we developed. This is a live feed of high contrast synthetic image reconstruction during revolving upon cooling stimulation. Our method is to extract multiple synthetic image throughout the recovery processes. Then quantitative synthetic image contrast evaluation and its dependency on stimulation temperature that we have studied, right? We found that there is no significant, the effect of the stimulation temperature is not there. So that is positive. And then we also discuss potential application of our such high contrast improved vein visualization. What next? We can have further study on large cohort required. Right? So far, our sample size is 14, so that this can include the variability in age, weight, right, BNI, obesity effect, cooling duration. We haven't touched on the cooling. The cooling duration is we apply 30 seconds. Right? We can vary the cooling duration, for example, 5 to 60 seconds to see the effect of the contrast. Also the ambient condition, perhaps. You see, thermal property of the skin and internal thermoregulation change with age. That's why age effect is important. So with that, I conclude my talk. Thank you very much.
Okay, thank you very much, Professor Eng, for the very interesting topic. So now we are on Q&A session. So we are very welcoming all the participants to ask due to the time constraints. So we have a 1 to 2 question. So please raise your hand. Any
First of
question?
all, 1,000 apology for the poor recording quality. I absolutely apologize.
Exactly. Right. Yeah. The presentation, however, very clear. Yeah. So hopefully we can get the knowledge from this presentation. Okay. So the first question for me, Professor, related to the, because I also read your related papers. So the limitation, one of them is the duration of cooling application on the dynamic SI contrast, right?
Yes.
So yeah. So is for your future research, what is your plan in order to probably solve or propose the new method in order to increase the duration or another technique probably?
Yeah, thanks, Chair Khalid. Last time when we conduct this experiment due to the COVID lockdown, we spent 2 years to collect just 14 sample size because of the restriction that we have. Certainly now the observation based on limited, only less than 15 of the patients, but definitely need more cohort size. Duration is interesting. If we can establish the cutoff duration, critical stimulation, I think that will be essential so that we can minimize, optimize the process, right, to make the application more practically useful. For the setting, it depends, because for the vein puncturing, we need to be fast enough, right? Fast.
Yes. Yeah. Okay. Get it. Okay. Thank you, Professor. So is there an, okay, one question from Rose Leader, please.
Okay, good morning, Prof.
Good morning, ma'am.
Happy to see you finally here.
Thank you, ma'am.
Okay, from the presentation, I can see that you use thermography and the cannulation. Isn't it like that?
Yes.
Okay, one is invasive, but the cannulation is invasive, but thermography is non-invasive. So how can we deal with these two things? And the second question is about your research. You have a cohort research. How could you conduct this kind of research? Because we are doing research in thermography too, but it seems so hard to do that. Thank you very much.
Right. Our approach is hopefully you can view the vein accurately. Then before we do the cannulation, like those drug administration, all this, so that better successful rate. So that is one thing. The other thing is for the just now your second question is what challenging, is it, on this
The challenging in doing this
I see.
thermography research.
I see. Okay. Actually, this
Find
work
the
is,
pressure and everything.
I see. This vein visualization project is, in fact, it's spin off of the other project. The other project, we look at the carotid artery blockage, stenosis. So we're using this stimulation also. We can able to find the blockage underneath the skin using active thermogram. So with that, we thought it's very promising to look at the vein puncturing also. And this one is a side branch of it. So, is challenge in the sense that we need a lot of IRB approval, but especially COVID lockdown and the duration of the project also limited. So we struggle for it. Yeah. I'm not sure what I saying is useful to you.
Okay, thank you, Prof.
Thank you, everyone. So sorry for overrun the time.
Okay.
No problem.
Thank you very much for the participant. And Professor, last but not least, for your information, so there is one research group in our department which also work on the thermal imaging. So we expect the further collaboration in the near futures between our universities. So this is our hope for the future.
It's my honors. I'm looking forward for your email so that we can link out and then share some of the work.
Okay, sure,
Yeah.
sure. Thank you very much.
Thank you, everyone. Thank you.
And yeah, so as the appreciation, we will also deliver all the certificate for the keynote speakers after this conference done. And because the time again, let us give the applause for Professor Ang, and back to our MC, Fira. Thank you.